Want to see the delay? How much delay do you have?
Yeah, there was. You see the very.
Put this up.
Yeah, but I think she was telling me she's so there's like. Yeah, I just don't watch.
So wherever you would like.
Hello.
You know,
Did you see Tomas's email?
oh my gosh. That's insane.
Like Monterey.
That's some of the worst I've ever heard.
Yeah.
Maybe some of them you don't know. And it's such a pain.
It's a pain. Everybody's suffering, essentially, except those very few in the end who eventually get funded.
Yeah.
Good. Writing it, submitting all this stuff, suffering.
It was a frustrating. Oh well.
I was hoping that, since it's fundamentally for us, whatever people want to listen, it's also, it was very big, so I bet it's all over the place in terms of what.
Oh well.
Well, I think it's in the bubble, so you know, I don't know what goes well and what doesn't. But there's 20 panels, so each of them can only recommend one, and then out of that, they need to what is dinner?
That's right. Really for dinner. Just eats all the time. Optimistic.
Or you eat all the time, yeah. Like,
I didn't have enough breakfast.
fruits, yeah.
Yeah, so it's a presentation.
The light.
Oh, it's like reflecting.
And the only thing that makes sense is that it's a room afterwards.
It's
There's certain achievements around it. That's why
the screen. I mean, that's the screen that's like real.
yeah.
I don't know if it's.
Oh, wow.
That's not right. It's also very reflective.
I didn't even notice that.
It's I think it takes this. So Oops, sorry.
Now you can go on.
Tom, can I just yell into Thesis?
Hi, nice to meet you.
So you might have signed a letter or something. He's now visiting. He's living.
It's been like this
Well,
for a while.
He's now living in the United States.
Yeah.
What do you call it? He won the lottery. Got a permit to come here. So he's looking for back. And while he's doing that, we're
You're not a snake, but just scripting.
That's the freedom you gain from teaching. And you're bad.
Do people pay?
I guess just
Not even or
Okay, I'd like to start somewhat on time. Thanks a lot for all showing up. It's my great pleasure to introduce Anna Scott's thesis presentation. Anna did her undergraduate at University of Chicago, majoring in mathematics, then did a master's at Taos in applied math, and then she's been here, I guess, 5 years. And she's going to be talking about some work that she's been doing, trying to understand the urban heat island using observations and modelling. On the side, separate from her PhD, she's been slightly distracted with developing air quality sensors, and she got an EPA Smart City Challenge grant, and her and her other students and postdocs have developed a low-cost air quality sensor, which they've been putting around Baltimore, and just last week gave one to an undergraduate who's taken 6 of them to Uganda. So she's managed to do that, as well as her thesis work, and probably even more significant is she managed to get me out in the field for 1 day. And
on his bike.
I was in the field. I wasn't doing anything, but at least I was out there. And I've just come back from a visit of colleagues in NOAA in Boulder, and I told them I had to come back because of the thesis presentation. And when they asked what the student was doing, when I said that she was taking measurements, a couple of them fell off their chairs. I then had to calm them down and say I had nothing to do with it. So, Anna has all the responsibility for that. So anyhow, Anna, take it away.
Thank you, Darren. And thanks everyone for coming today. How is this supposed to work? So today I'm going to be talking, as Darren mentioned, about improved understanding of the urban heat island, and we'll get to what exactly that is. But our story starts today, at least in Chicago, in mid-July 1995. On Wednesday, temperatures started climbing to about the high 80s, low 90s, and the humidity rose as well. And over the course of the weekend, temperature and humidity grew and stayed, and it ended up killing several hundred people, so many people that morgues actually couldn't keep up. So here's a headline from, admittedly, one of the more sensational Chicago newspapers. But certainly, you know, when you read interviews from the morgue officials, they had no idea what was going on, and they didn't understand really what was happening. And when the epidemiologist came in and did the final counts after, you know, the heat event was over, the death toll actually was as high as over 1,000 people who died. And most of this death toll was concentrated amongst elderly people, particularly Black and Hispanic populations who live on the city's south and west sides, who couldn't afford air conditioning and lived in crime-ridden neighborhoods and were afraid to open their windows, and also weren't aware of some of the risks that heat would pose. So this was certainly a real surprise and wake-up call to people in the cities. Fast forwards to 2010 in Russia and Eurasia. Here I'm showing temperature observations from NASA, who conveniently left off the color bar. But the dark red and dark blue colors here are about plus or minus 12, so red is hot. And what this is showing is the average sustained temperatures over the summer were really, really high. The death toll for the summer was like 10,000 people. That's 1,000.
And again, when people crunched the numbers afterwards and started to wrap in all the other things, sort of the extraneous deaths that were killing people, including like drownings and traffic accidents, all the things that didn't occur in cooler periods, the death toll rises to about 40,000. This is an image from 2015 in Delhi, where heat wave is so hot that the streets are literally melting. I think this image was from the year after that one of our colleagues visiting here at Earth and Planetary Sciences told us that heat was a first world problem, and then went back to this. More recently in the news today, or this is an image from yesterday in Karachi, there's above 100-degree temperatures that are really stressing vulnerable populations. And so together, what all of these anecdotes demonstrate is that extreme heat is one of the deadliest forms of climate hazard. And so here I'm showing an image from the World Meteorological Organization's Atlas of Mortality that aggregates deaths by decade by weather and climate hazard type. Extreme temperature is shown here in orange. And I think when you think often think about like weather and mortality, we think about some of these extreme events like hurricanes and big droughts that are really sort of catastrophic, but also can happen in short periods of time. But extreme temperature is actually one of the rising, is a significant burden of sort of weather and climate-driven mortality worldwide, but it's also an increasing one. So whereas in past decades it presented less of a problem, this is the data from 2000s, and it's certainly something that's going to be growing in the next decade, the next time they do these statistics. This is a problem in a world in which temperature and heat extremes are projected to increase. Here I've reproduced a plot of temperature observations and models. The colors here are hindcasts from the AR4 CMIP 3 runs. If you don't know what that means, it's not totally important. But generally the idea is that as we go forward in time, we're projected to get hotter, and the same thing is projected for heat extremes, which are expected to increase in both frequency and magnitude. It's possible, some have suggested, that extreme heat may be exacerbated by a phenomenon called the urban heat island, which you've heard mentioned in the title of the talk. Here I'm demonstrating this from a land surface temperature satellite image of the city of Baltimore. So this is a bird's eye view from a satellite that has a thermal camera, and so is seeing the temperature of the ground. Here is a map. This is where you're located, for those new to town. This is the Inner Harbor. Hopkins is, let's see if I can do this here, where it's a little bit cooler. The thing you'll notice from this image where darker red colors indicate our higher numbers and hotter temperatures is that the city exists sort of as a sea of red, and outside of it, is an island of red, and outside the city is a sort of a sea of cooler temperatures, which gives us this phrase name, the urban heat island. In this talk, I'm going to be sort of simplifying how we refer to the intensity of the urban heat island by using a pretty simple metric we're calling delta T, just the difference in temperature between an urban station and a rural station. And so to ask the question why urbanization could change the weather, why building a house would be the weather to change, we have to understand something about how the physics, I guess, of the lower atmosphere works. So sunlight is the primary source of energy for most of the part of the Earth that we live in. It travels through the atmosphere, which is transparent to radiation. Some of that radiation gets reflected away. Some of it gets absorbed and re-emitted as long-wave radiation. Together we call this RNet, or net radiation. In addition, the energy that gets observed at the ground is released as dry or sensible heat, and as latent heat is evaporation. And together these terms are balanced. The remaining energy goes and gets stored into the ground. And so together this sort of physical basis means that when you alter the urban surface by putting up buildings, you pave paradise, and you put up a parking lot, you get modification of the surface geometry and then surface properties. So first, and this is in no particular order, but you get the absorption and trapping of sunlight at low angles. You get air pollution that's trapping heat generated from factories, cars, etc. You get the trapping of heat as it tries to escape from the surface, so that long-wave radiation gets trapped in these long, narrow urban canyons and can't escape and radiate to space. You get anthropogenic heat, which is simply just your car, your air conditioner, your refrigerator releases heat into the lower atmosphere. The material properties of urban areas increase heat storage, so there's more material there that's more able to hold on to heat. You decrease evaporation by reducing the amount of vegetation, which here is ironically shown by a tree. And then finally, the decreased wind speeds occur because of, again, the irregular surface geometry. This is a problem in a world that's rapidly urbanizing. So urban populations are growing. Now we live in a world that's more urban than non-urban. But this is a trend that's expected to continue on through 2030 and into the future. And so altogether, this means that quite possibly urban populations may be uniquely at risk for heat, which makes it important to understand this problem. And this has been suggested in the past. This is a 2013 paper from Van Lee and Ali Gouzaid, who showed in their paper that heat waves make cities swelter synergistically. A lot of corporate speak on that one. This is the figure that they use to sort of pin that down. They're showing two time series from two weather stations here in Baltimore. So DMH is the Downtown Inner Harbor Science Center weather station, and BWI is the airport station. So they looked at this period, I think this was 2011, in June, and they saw that as time went on, the average of the temperature difference between these was higher during the heat wave than it was after the heat wave. We maybe took issue with some of those findings, but we'll talk about that a little bit later. So in this thesis, I'm trying to ask the question, a couple of questions, I think, that get at improving our understanding of urban heat islands. It allows us to sort of prepare for the coming health challenges. So first, I'm going to ask, how does temperature vary within the urban heat island? Second, I'm going to ask how urban temperature varies during heat waves. And then third, I'm trying to get at what causes this variability that we see, not just between urban and rural areas, but even within cities. Specifically, I'm going to ask this question by focusing on a couple studies. So first, I'm going to look at how temperature varies in Baltimore, Maryland. Next, I'm going to do the same thing for Nairobi, Kenya. Third, I'm going to ask how urban-rural differences vary during warmer conditions. And then finally, I'm going to ask the question of how well numerical simulations can capture this variability. So first, thinking about Baltimore, this chapter asks the question how temperature varies within a thermal hotspot in Baltimore. And what do you mean by that, you say? So this is our land surface temperature image of the city of Baltimore that I've shown before. What we noticed when we looked at this image, which is something that urban planners have used in the city, is that you get this really sort of like extra hot zone that's here in East Baltimore. And it's somewhat surprising because you might think, oh, well, like downtown where you have really tall buildings and where development might actually be a hotter point in the city. But instead we found that this hotspot was displaced. So we worked with the City of Baltimore's Office of Sustainability to ask the question, what was temperature variability like in this pretty constrained zone where it looks like from satellite images that it was really hot? We did this by using some low-cost thermometers. I don't have one of these on me. I'm sure there's one like lying around on the floor here. This is called an iButton. It's about the size of a small watch battery. And working with some of our colleagues from MICA, Ben, developed a radiation shield that allowed us to sort of put these instruments out all over the place and really expand the amount of measurements that it's possible to take. We deployed these all over the city. Here are some sample images, one showing this in a park. It's hidden up in a tree. One of the features of this is it's not so obvious. If you've seen a traditional weather station, they have a tripod, they have like whizzing, whirring things, and they have like solar panels. It just kind of like screams like weird science, steal me. It's not that these don't, but they're just harder to find. So here's an image in a park. This is one of our interns, Dylan Ponzo. And then here we have the instrument in a tree in a neighborhood in East Baltimore, in a residential area. So the first question to ask when we're using sort of novel low-cost instruments is how well do they work? So here I'm showing evaluations of our instruments called iButtons, both on the left at here, like on the roof up there at Johns Hopkins, and on the right at the downtown station in the Inner Harbor. So that's located right next to the Science Center. This is only looking at morning temperature, so we're looking at minimum daily temperature, which occurs around 6 a.m. And the reason we did this is we admittedly had a lot of problems with the error in the daytime temperatures. And so we found that the agreement was pretty well here. If you're looking at, so this area, the gray area is the accuracy of the I button. The boxes show the distribution of each of these I buttons. And what we found was, for the most part, there's some variability in the sighting of these buttons at Hopkins. We can get into like, what sort of, how you can sight instruments on a roof versus sighting them at the ground level and shade a bit. But the ones we had at the Science Center, which we thought were consistently sighted, all fell pretty close to zero mean difference between the standard instruments and our instruments. So we said, okay, this is great, let's proceed. And we put these out over Baltimore. So here is a map showing 135 of the sensors that we have located, in the city of Baltimore in the summer of 2015. Give you an idea of scale again. This is the Inner Harbor. We're up here at Hopkins. This is a kilometer. What we saw was that there was actually a little bit of spatial variability throughout our study site. So temperature did vary, air temperature did vary throughout our study site. And in particular, when we looked at the histogram and time series of the data, we noticed that there were some differences. So on the left, I'm showing a histogram or relative frequency. So we rescaled these histograms to reflect the fact that there's an uneven number of samples between all of the data that we disaggregated. So looking at this histogram, we said, okay, all the data is shown here in purple. You actually can't really see it on this plot. But the impervious data, so data that was come from thermometers at impervious sites, is shown in orange, and then data that comes from green spaces is shown in green here. And what you see is there's really a lot of variability in this plot. But on average, sites that were located in impervious locations were just a little bit hotter than those located in green spaces. This difference was actually statistically significant. If you're wondering how could that difference be significant, we had a lot of measurements. When we look at the time series, we see that this difference is pretty systematic throughout the summer. Again, orange is the impervious sites, green is the green spaces sites, and we notice that these differences persist throughout the summer. And we also note that sites with vegetation are a little bit cooler than the downtown station, but impervious sites are actually a little bit warmer than the downtown station, but the mean difference with the station is actually pretty trivial. I mean that in a statistical sense. So we saw that there was a little bit of variability, and so we asked the question of why. And here I'm showing all the results from the thesis, but I think that's maybe not the point of this. So here, if you're interested, I can walk you through it. We're showing on the y-axis is always temperature for green spaces, impervious versus elevation, albedos, reflectivity, jumping over here, distance to a park, tree canopy, so the percentage of trees in the area, and then we did the same analysis for impervious. And we looked at the correlation, and we looked at the corresponding p-value, and we found that the correlation was significant for the relationship between temperature and elevation, ditto for albedo, should be tree canopy, not so much the distance apart, but this showed us that surface properties explain some of the surface variability for vegetated sites well, and when we put this into a regression, we found that the explained variability in all this was a little bit higher than like 60%, give or take. When we did the same analysis for the impervious sites, which actually turns out to be much of the sites, we didn't find those relationships, we did not find that those relationships held up. And so the surface properties could explain the variability of vegetated sites, but less so for impervious sites. So what we've seen from this part is the temperature observations within a thermal hotspot in Baltimore have shown that the spatial variability in minimum daily temperature is pretty small. There's some spatial variability that gets explained by surface properties, but again, that's not all of the data. And finally, sites with vegetation are cooler, but really cooler just sort of by a little bit. So next we moved on to doing a similar study in Nairobi. In this part, I asked the question, how does temperature vary in informal settlements in Nairobi, Kenya? So informal settlements are a type of neighborhood that legally don't exist, which means the residents there don't have access to really any legal service, including like plumbing, electricity, et cetera, et cetera. Things are changing now, but they've also been trying to change things for a long time. And so in some sense, these are kind of analogous neighborhoods to the ones that we looked at in Baltimore, where we have policymakers and disaster relief agencies who are concerned about possible impacts of heat waves. You know, if you're interested in the impacts of heat waves and you have like a certain finite amount of money to spend, you're not really interested in understanding how those dynamics play out in neighborhoods where people can afford air conditioning. And so these would be the neighborhoods where people can definitely not afford air conditioning, for example. So we looked in 3 neighborhoods. We looked in the neighborhood of Kibera, Nakuru, and Mathare. This is the city of Nairobi. It's located about 1 degree south. And here I'm mapping the land surface temperature in purple and the mean air temperature from our study in red colors. And I think the thing to note here is coming from the last chapter that we looked at, where we saw that in Baltimore we had these like thermal hot spots in the center of the city, and like to first order, the more people that were around, you sort of had higher temperatures. In Nairobi, we didn't see that to be the case in the temperatures, and so that's an interesting difference. So here's what this is the neighborhood of Kibera. This is what our study sites generally looked at. Here's a picture sort of once you go amongst the houses. Houses are generally built pretty close together. They're built of very different materials than they are in the United States, and a lot of it's whatever people can find around. And there's also a lot of variability in some of these places where people have like firmly middle class homes to people who really are sort of just really scavenging for whatever they can, like wood, sheet iron, or whatever, to sort of get a roof over their head. I should point out, this is the corner of Osh's face. This is our undergraduate intern at the University of Nairobi, Jerry. This is Otin. I don't know. Herbert might be hiding in here somewhere. So we did the same thing. We took the eye buttons and the little houses. This is around Christmas time, so people thought that they were Christmas trees, which really works to our advantage. Here, I've installed one of the instruments at the Kenya Meteorological Department's headquarters. So their instruments are located inside this Stevenson screen box to sort of do that same validation that we did in Baltimore. And then here's a typical installation in a household. So see this here. We sort of stuck those instruments underneath the eaves of roofs, which were the best attachment site we could find for them. In Baltimore, we've really been sticking things to trees, but in these neighborhoods, there's no trees. So, and there's also very little, again, infrastructure like poles or posts. So this is sort of the best available. This is the best available siting. It's also something that was pretty consistent throughout our study. Like most of the sites where we attached these thermometers looked pretty similar to this. So again, we evaluated the thermometers. So on the left, I'm showing the difference with the station for each of these different category of measurements. So minimum daily temperature, 9 a.m. and 3 p.m., as well as maximum daily temperature. It's worth noting that Kenya Met, they're still using analog instruments, which means that their hourly measurements come from a different instrument than does their minimum maximum measurements, which comes from a min-max thermometer. I'd be happy to explain more about that later. So here's the evaluation that we did for temperature. We did a similar evaluation for relative humidity. The eye buttons also measure humidity. What we concluded from this is that the minimum daily temperature measurements agreed pretty well. The 9 a.m. temperature measurements agreed really well. 3 p.m. was like, and then Tmax was sort of like, oh, that was a thumbs down. But because maximum daily temperature in our measurements occurs around 3 p.m., we sort of said, okay, this discrepancy doesn't make much sense. We're, the hourly measurements are only missing Tmax by, maximum of like 30 minutes. So what we decided to do is we said, okay, like this bias is acceptable. Like this is a bias of, it's less than 2 degrees. We'll just subtract off that difference from our measurements. We're looking at mean measurements for the most part. And we'll use that to sort of tie in our eye button network with the meteorological station. So once we do this, we get these results for minimum and maximum daily temperature. So again, this is a map of Nairobi. This is on the left, we have minimum daily temperature. Again, the purple is land surface temperature, but not important for this. And then on the right, we have maximum daily temperatures. And the point here is that temperature does indeed vary spatially in Nairobi's informal settlement neighborhoods. And more importantly, this yellow dot here, that's the central weather station. So if you're tasked with monitoring what's going on in these neighborhoods, and all you have is a weather station that's located right here, you might not be capturing all of the conditions that people are experiencing. And again, this is one of the most health vulnerable neighborhoods, frankly, in the world. So understanding this difference can be important, as we'll see. And so to give some meteorological background for what's going on, we did this in 2016, which turned out to be an extraordinarily hot year. And the temperatures exceeded a number of historical thresholds. So here I'm showing the temperature we measured from the neighborhoods in the dotted, these 3 dotted lines. The dashed line here is the temperature we measured at the station. And then the historical threshold shown here is the 95th percentile of historical temperature for minimum and maximum daily temperature down here. And what you notice is that we're really high above those temperatures, and we're above those temperatures for most of the year. These are corrected. You guys see the question on space. These are corrected to adjust for the mean bias with the station, which doesn't necessarily have to be a linear correction, but the fact that we're several degrees above it, I think, starts to get at something. So when we looked at mean temperature by hour, here I'm showing the average temperature in each neighborhood each hour for the summer period, 2015. It's equatorial, so summer is maybe not that meaningful, but it was in November. It was a December, January, February, so it's DJF. For the neighborhoods and the meteorological station in the dashed line here, I put error bars in here showing the sensor standard deviation, which here represents the spatial variability we see. And together this shows the temperature is higher in informal settlement settings. We then computed the heat index by neighborhood, so that combines the temperature and the humidity together to get at a measure of heat stress. And again, what we saw was that it's consistently higher. There's more heat in these neighborhoods. And so one question is like, okay, well, we're really talking about temperature differences of only a couple degrees. Do these differences matter? And maybe to some folks, they don't. But what we did is we looked through the health literature and we said, okay, like how can we tie this in to health data, which short answer is we can't. But there have been a couple of studies that have looked at mortality sort of throughout the city of Nairobi and tied that into weather variables. And so we used the thresholds that they found in those previous studies where they had found a connection between heat and health. And I'm showing that here in this like solid line. And what we found is, for the most part, while the station sort of bounces around below that threshold, a lot of the temperature in the neighborhoods actually exceeds that temperature. And because health is very nonlinear, and these heat-health relationships are similarly nonlinear, these small differences could actually matter quite a lot. But again, it's hard to say exactly because these measurements come from different meteorological stations. And I know, we worked with the Red Crescent Climate Center on this one, and they sort of wanted us to do an analysis of like how many people this possibly impacted and what would have been the excess mortality. And we finally said we really don't think we can, but what we can say is that this definitely calls more work to be done. And so, what is causing some of this variability, like between the neighborhoods? Because it's all good to say like something's bad, but how could you maybe think about fixing it? So the first thing we did is we looked at understanding what's the relationship between the land and the atmosphere. And we did this by looking at the surface temperature, so those purple maps that I've been showing people. And taking, at each site, we take the surface temperature, and then we take the air temperature. And we did this for the average daily temperature. We did this for the minimum daily temperature. And then we did this, oops, I'm not getting this, there we go. Thank you. Min, max, mean. And what we saw is that at all hours, there's a correlation, but that correlation is strong and significant mostly for during the daytime hours rather than the nighttime hours. And so that's an interesting flip of what we had seen in the previous study in Baltimore. And so here, I think the details of this figure probably aren't important, but if you're interested, we looked at mean daily temperature, which again correlated with surface temperature. We correlated it against land surface temperature, elevation, NDVI, which is a satellite index for vegetation, albedo, which is reflectivity, and then just the presence or absence of whether or not we physically saw any greenery when we were installing the monitor. And what we found is that mean daily temperature is indeed correlated with some of these ground properties, especially the ones that have to do with things like vegetation. And so to conclude this chapter, we looked at temperature measurements in informal settlements in Nairobi, Kenya, and we've seen that temperatures in informal settlements exceed the temperatures measured at the central weather station. We can partially explain some of the spatial variability by surface properties. Sites with vegetation are cooler. Oops, and finally, which got left out, these differences were enough to possibly have health consequences. So next, we move on to looking at the urban heat island intensity under warmer conditions. And so the question I'm asking in this chapter is, how does temperature differences vary during warmer conditions? Which here, I think, if this is very big, you can maybe just think about heat waves was the question we wanted to get at, but we wanted to think about heat in a variety of ways, because there's a variety of ways that it can be hot. It might be hot day to day, it might be really hot week. So to ask this question, we return to the United States. I'm using the GHCN network. I pulled station data from 53 cities, and I paired each station to be an urban station and a rural station according to a satellite brightness index. Here, I'm demonstrating this in Baltimore. This is Inner Harbor, and it's Baltimore. But here, the white color indicates that the satellite's seeing brightness or urban areas, and then the dark color indicates rural areas. And this is sort of the pair that it finds. It finds BWI as an urban station, and then it finds X3 outlet stations. This isn't the final station that we use in the study. This is just an example. And so using this data set, we were able to ask some sort of basic questions. For example, like, when are these temperatures greater? Some folks have suggested that they're almost always greater at night, and some of our favorite reviewers have had some things to say about that. So here, I'm showing the temperature difference for minimum daily temperature minus the temperature difference for maximum daily temperature for all of the 53 cities that we used. And what you can see is, ta-da, all these colors are red. So we said, okay, great, we're going to focus our analysis on minimum daily temperatures. And we started out doing this by looking at Baltimore. So here, I'm showing a scatter plot of 1985 to 2015, so 30 years of daily summertime data. So that's JJ, June, July, August data from a rural weather station and an urban weather station on the y-axis. And what you can note here is that these points almost always lay above this one-to-one line, the dashed line that would be where data would lie if rural and urban temperatures were equal. And we fit a regression line through this data, and we find that the slope of this data point is less than 1, indicating that as you get hotter, generally this data becomes more similar. And so this sort of suggests that maybe on a day-to-day basis, as rural temperatures increase, urban and rural temperatures become more similar and not more dissimilar. In particular, we noted that this is due to sensitivity in rural areas rather than urban areas. So here I'm looking at a similar plot to the last slide, but I'm plotting it against the average temperatures, the average of urban and rural temperatures. So I'm showing average temperature on the x-axis and urban temperature on the y-axis. And the reason that we're doing this is if it's hot in any one given place, just by sort of randomness, you might expect that it would be less hot in a second place. So by averaging, we get rid of a little bit of that statistical noise that might possibly influence our results. So we did this analysis for urban temperature and rural temperature. And once again, this dashed line is the one-to-one line. The data lies above it, which indicates that it's hotter in urban areas than it is in urban rural average. Surprising. And we sort of look at the slope of this curve. It's 0.99, which is pretty insignificant. But by contrast, when we do the same for rural temperature, which here lies below the one-to-one line, we get a slope that's larger than 1, which indicates that it's becoming more similar. And so we conclude that this phenomenon is driven mostly by sensitivity in rural areas rather than sensitivity in urban areas. We repeated this analysis for each of the 53 cities that we looked at in our study, and we focused on this regression coefficient right here. And this is what I'm showing on this slide. So here I'm showing this data as a histogram, and here I'm showing it mapped out. And again, this is this regression of the regression coefficient of function of rural temperature as a function of urban temperature. What these colors show is that by and large, urban and rural temperature become more similar when rural temperature, average temperature, rises in the United States. We can see this because this average coefficient is about 0.88, which in this case indicates that urban and rural temperatures are getting more similar. And so there we looked at this on a day-to-day basis. Now we're going to look at this in terms of heat waves, which again, this is a big policy priority for a number of people. So we went back through the temperature records and we pulled out 15 of the hottest nights that we could find in the record. We made sure that there weren't any duplicates in this, which, man, fingers crossed, that worked. And so we centered them around the hottest day. So we called this a heat event. So we went from day -4 to day 4 and looked at how temperature got hotter and then stopped getting as hot. Each of these events, look at the date here. So we looked at the temperature and then we calculated the temperature difference between the urban and the rural areas. And we took the mean of all of those 15 events. And what we saw was that despite suggestions in the literature that these differences were supposed to get like hugely larger in a way that like meant that cities really needed to be way concerned about urban heating or heat waves, is we saw that like not only was it pretty flat, like I don't know, on average it almost decreased, and then in some of these events it like decreased a lot. So we concluded from this that during Baltimore heat waves, delta T stays constant or slightly decreases. We repeated this analysis for all the 53 cities in the sample size. And so that average line I'm showing here. So again, this is temperature, and this is temperature difference over the course of 15 heat events, average. And what we see by and large is that, yes, it gets hotter during heat waves, not surprising, but the temperature differences, for the most part, don't actually become that much larger. And in most cases, they actually slightly decrease. In many cases, they just stay constant. And this was a pretty novel finding. Nobody had looked at this in a systematic way. A lot of the studies that people had done really sort of focused on a model, and they hadn't, because of that, they weren't able to look at events over several years. And I guess it should be mentioned that we've repeated this analysis with data going a little bit farther back, using 60 years of data. Temperature observation data in the US had some instrument changes that took place over the past like 3 years. And our reviewers suggested that we remove that data, but this finding seems to be pretty robust. So we, or rather our reviewers, asked the question of what causes this. And I'm forewarning you, I'm not going to give you a satisfying answer today. But what we were able to do is we were able to relate this to synoptic or large-scale weather conditions. And so here I'm showing in the left panel, I'm showing temperature differences, that's correct, on moist days versus dry days. And what we see is that temperature differences are different. They're lower on moist days and they're higher on dry days. When we move over here and sort of disaggregate all that and look at it, we see that the temperature is hottest in urban areas on moist days and less hot on dry days. It's a little bit less hot on moist days, and then it's like really a lot cooler in rural areas on dry days. And so we take away two things from this. First, that the effect of decreased temperature differences during warmer conditions is most pronounced on moist days. And that second, it's due to sensitivity in rural areas, which going from rural areas when they're dry to rural areas when they're wet really can't cool off, particularly at night. Again, this is nighttime, sort of 6 a.m. temperatures. And so we asked the question, okay, we've seen this effect over space. How consistent is this? Do we see this? Sorry, we've asked if we've seen this effect over time. And so we wanted to ask, is this widespread? And so we asked the question of, do hotter cities have smaller urban heat islands than cities that are less hot? And so we looked at this in a couple of ways. We looked at rural versus urban temperature, and then we looked at understanding how this worked by comparing urban temperature to the average temperature, and again for rural temperatures to get at that sensitivity. So here on the left, we see for time mean temperature for each city, so it's like a 30-year summertime average temperature. We see that for the most part, urban and rural temperatures grow to be more similar as it gets hotter. So that's a yes. We move over to this plot and we look at urban temperatures compared to average temperatures. And we see that the slope of this line is, again, it's about 1. So the urban areas don't appear to be changing that much. When we look at the rural areas, we see that the slope on this regression is a little bit greater than 1, which seems to suggest that there's something going on, again, in rural areas in order to drive this phenomenon. So we looked at station observations in 53 US cities for the period of 1985 to 2015. We've shown that urban-rural temperature differences decrease during warmer periods. This includes both daily variability and heat waves, as well as between city to city. So this effect holds for warmer cities. Second, we've seen that this decrease that we've observed is driven by sensitivity in rural areas. And then finally, I don't know what to do about that. Finally, lower temperature differences have been linked to synoptic weather conditions, and we think that the moist conditions affect the rural areas, which cause this effect. So finally, we'll move on to looking at observations and models, and be returning to here in Baltimore, Maryland. So in this section of the thesis, I asked the question, how well can we capture urban temperature variability, both in observations using the microclimate techniques that we've developed in the first sections, as well as models. And so first, the model that we'll be using for this is the Weather Research and Forecasting Model, or WRF. It's a numerical weather model. It incorporates the fully incompressible non-hydrostatic Euler equations. There are subgrid scale processes in this model that can't be resolved because of the resolution we run at, which in this case is a kilometer. These are parameterized. Those interested in the setup of the model, mentioned it's a 1 kilometer resolution, where we nested the model. We'll show that in the next slide. And some of the options we're using is we're using the urban canopy model with an SST update, as well as a 40 land class use, which I'm demonstrating here. Most of those land classes, though, aren't really applicable to our study. So this is our model setup. Again, we ran this one-way nested for a couple of different domains. So here's our outer domain. That domain drove the boundary conditions for the inner domain, the middle domain, and then again for the inner domain. And so this third domain was the 1 kilometer resolution domain, and in this little box here, that's where we're focused on in the city of Baltimore. In their study area, there's a couple of land types that the model represents. So first is high intensity land, second is medium intensity land, low intensity land. There's open space, there's some rural forests, and then there's water. And then there's a couple other points that are like marshes and bare rock. We compared these model simulations to temperature observations that we took in 2016. So here I'm representing those in little triangles. I've centered each of the observations in a model grid box cell. Some of the I buttons are located in the same model grid cell as another I button. And the average for that is about like 5 or 6. So once again, we've returned to this issue of how do we take temperature in urban environments. There's a lot of challenges. And so again, we did our station evaluation. So here on the left, I'm comparing an I button to the weather station, again in the downtown Inner Harbor, at all hours at 6 a.m., minimum daily temperature, 4 p.m., and maximum daily temperature. And you can see for the most part, the temperatures, like the distribution of the temperatures more or less stack up. When you compare these two in part B, where I'm showing the distribution of the difference, we see that these differences for sort of morning temperatures are small. They're less than ½ a degree. But once we start getting into the daytime, we start to see larger errors on the order of like a degree and a half, which starts to be significant. And so here I'm showing the same data by hour. So here, hour and temperature for 2 of the instruments. And what we see is the diurnal temperature cycle is not only slightly different, especially it's higher during the day, there's a little bit of an offset of this cycle. We think that's because our instruments are pretty open, and so they cool off faster, and they can, well, they get hotter faster as well. So what we did is we took this difference and we just subtracted it off from everything in order to account for potential instrument bias. And we think this is a pretty reasonable approach because in this study, we'll only be looking at mean temperature rather than time varying temperature. I mean, except for the hourly measurements, but that in itself is a mean. So we took the distribution, the statistical distribution of all the temperatures that we observed, shown here, and we disaggregated them by the land type that they were located in. So these were sensors located in high intensity land, medium and low intensity land, combined open space, and then rural forest. And we compare these in the study to the same data from the model. So if we have a point located in the model, we just take the nearest grid cell, and we take that as a comparison. And what we see from looking at this is that looking at, so this is, this should be more 6 a.m. temperature, and then this should be 4 p.m. temperature, correct? And what we see from this plot is the temperature varies by land type, and in particular, more developed land types, which here I'll be showing in bright colors, are hotter than those. So these are our observations. There's a lot of spatial variability. You know, it's hotter for the most part in this land type, but there's overlap between these different land types. So if you're in high intensity land, on average, it's hotter, but you could be located in what's considered like a medium intensity land use, where it'd be even hotter than a higher intensity land use, and et cetera, and so forth on down to the different land types. When we compare this to the model data, we see that the model does get it right, that it's hotter and higher intensity lands. It would have been almost impossible for it not to get this right. But we noticed that there is some differences in particularly the width of the distribution. In some cases, this isn't totally surprising. A model, in some senses, averaging over a kilometer box, whereas our thermometers are taking measurements really closely, that reflects like a cubic meter or something of air. But this has some implications for how you might want to use the model. And so this is a lot of statistics, but when we evaluate the model by subtracting the model, the observations from the model, what we see is that if we do this in a way that most people are doing it in the literature, it suggests that the model is actually performing really well. So here, I think it's most important to look at the root mean squared error. For all data, for hourly data, we get about an error of about 4.6. That's in degrees, so that's not phenomenal, but it's actually just at the upper end of what's been reported in other studies where people have been like, yep, check the box, this model works great. We find that there's some variability when we look at this at 6 a.m. versus 4 p.m. We see errors higher at 6 p.m. And ditto for min and max. And so, maybe these don't look great, but the point here was that other people have looked at similar statistics and they've said like, yep, this model works terrific. Like, this is a great time to like do my modeling study and tell policymakers what they should do. So we've seen that there is some variability within this model. One question that we've been asking is, can we attribute this variability to surface properties? And we've shown in the past how a lot of that surface variability in Baltimore is driven by vegetation. So one question is, are we picking this up still in our micrometeorology network? And are we getting the same thing in the model? And so here, this is new. I've dropped. I did that thing you asked. Here, we're looking at vegetation on the x-axis versus temperature. This is a vegetation index from a satellite called NVDI that we've seen in the past. And on the right is the equivalent of vegetative fraction that comes in the model. That's just a thing you look up. So what we're seeing in this relationship here, when we're looking at vegetation versus temperature, we correlate the data, and you can see pretty generally that as there's more vegetation, it tends to be cooler in the sites. Not surprisingly, that corresponds more or less with the land types. So again, the red dots are from, this is incorrect. The red dots are from developed sites. Orange is medium sites. Red is open space. Green is forests. We see that there's a negative correlation between these two. So if there's more vegetation, lower temperatures. And again, this is 6 a.m. and 4 p.m. So when we do that same analysis for 4 p.m., we see that there is a decrease of temperature with more vegetation. So that's what we see in our observations. We see this connection between vegetation and temperature. When we go over to the model, granted, like the model doesn't have a realistic representation of vegetation. That's probably to be expected. Again, we're looking at a much smaller scale, potentially, although NDVI is also a satellite product that exists at a similar scale to the stuff that we're drawing from in the model. What we see is that, we get these correlations, they're there, they're statistically significant, but the distribution of that relationship really just doesn't look realistic. And so, in some sense, you could sort of advocate for like, okay, well, we see a relationship in both observations and models, but if you're using these models to drive policy decisions, which a lot of folks are doing, they sort of are evaluating these large-scale greening policies, this to us raises more questions than answers. So one thing we're able to look at a little bit more in our observational data that doesn't exist in a model is how well smaller scale green infrastructure could affect temperature. So if you're a city like Baltimore and I tell you, okay guys, like build more parks, let's go. People are like, okay, great, like where do I get the park money? And you're like, oh shoot, like I guess I can't help you. You know, that's not super helpful. If you say, hey, like, you know, what are some things we can do at this scale at which we can operate, that starts to be a little bit more helpful information. And so here we looked at a couple types of green infrastructure that exist in Baltimore or you know, either in policy to increase or like at a policymaker's disposal. This includes street trees, so it's literally a tree on the street. Parks where there's trees, parks where there's open fields, and then urban forests. And so the difference between, I guess, parks and trees versus an urban forest is an urban forest is natural. It still has sort of the soil canopy intact. I'm not using the right language. Your Kathy's going to correct me later. But you have more of like a natural surface, and you know you have an ecosystem. And generally, they're a little bit larger than street trees, which are pretty young and small. What we found is that small-scale green infrastructure also affects temperature, and that these differences are seen between land types, which is exciting because it means that you know you could put trees in more developed parts of a neighborhood of the city as well as other parts of the city. You might notice that these get really hot during the day, and you're like, oh, that sounds really hot. We've actually dropped these sensors that get that hot for most of the parts of the study. So you know this data is maybe a little bit less reliable, but the morning data here is. And one thing that we know is that these sites and parks with open fields actually seem to get really cool during the morning hours. And so they're really able to cool off at night when, as we've seen before, the urban-rural differences are largest. And there's also some health data that suggests that that's when you get a lot of, that's where you get a connection with health. But certainly during the day, urban forests are a lot cooler than some of these other sites, which is good news if you forests. And so the last question we're going to ask here is how well can we capture urban-rural differences, both with our micrometeorological network and our model. And so here I'm showing a temperature difference between all of the data disaggregated by land type in two sensors located in rural areas. Here, those two sensors were located in open sites, and here, these sensors were located in forested rural sites. And these temperature differences look very different. So here, I'm looking at the temperature difference on the y-axis at an hour of the day here, so 0 is midnight, this is noon. And we see that in this plot where we're looking at differences with respect to open sites, we sort of see the classical picture that we would expect to see. So we have these differences that are highest in the morning, they go away throughout the day, and then as soon as the sun goes down, temperature rockets up again. By contrast, when we perform that same analysis with our observations, where we subtract off the observations of rural forested sites, we don't see that at all. We see, in fact, that like the differences are lowest maybe around noon, but they're high in the evening, and they're sort of like high, and there's just really not a lot happening, which is somewhat surprising. It's not something that people would expect. We then turn to see if we can see these things in the model, see this phenomenon. So, you know, I think to first order, you could argue that like generally, it looks like the model is getting sort of the shape. It might not be getting the intensity, so the model underestimates the intensity of the urban heat island, and it definitely doesn't get the sensitivity to rural site selection, and it also doesn't capture the fact that there's temperature differences in land cover classes other than the high intensity land. So to summarize this chapter, I've shown that observations, I've used observations from a low-cost sensor network and a 1 kilometer wharf run. And we've seen that spatial variability in Baltimore temperature causes the UHI to vary by several degrees, depending on your land type. This variability is affected by land type, as well as green infrastructure. The model temperature has low evaluation statistics, but we think it poorly captures key drivers of temperature variability. We think that we can use these results from a modeling study and observational study to ask how well are we even able to answer the questions that we want to answer. So, for example, in this chapter, we looked at how the UHI intensity varies with distance. I actually didn't show you that. We looked at the relationship between urban temperature and land type, and we felt that we captured that really well in observations. The confidence for that in the model was not as high because we saw that there wasn't a realistic distribution. Next, we looked at the relationship between green infrastructure, which occurs on a spatial scale you can't capture with models, and we think that we did a reasonable job capturing it with observations. We did sensitivity analysis, and we think we've gotten rid of some of the possible bias. So we're going to rate that as high confidence. And then finally, we asked this question about when is the temperature difference between an urban and a rural site highest. And this is one where we sort of have to throw our hands up a little bit and sort of acknowledge that there seems to be too much variability between different types of sites for us to really capture this, either with an observational network or in a model. We think that possibly some of this might be fundamental physical differences. Certainly the differences we see are consistent with theory, where we see open sites have temperature that escapes more at night, whereas a forest may act a little bit more like a city at night in that it can't radiate out heat. So far, we've shown the temperature variability in a Baltimore hotspot is small. Next, we went to Nairobi and we showed that temperatures in the informal settlements there are higher than they were at a central monitoring station, order of magnitude 5 degrees. We then looked at urban-rural temperature differences across the United States, and we showed that these become smaller when it gets warmer. On average, we found this to be true by about urban temperature only increases by about 0.9 degrees for every full degree the rural temperature increases. Then we looked at observations and models, and we saw that standard model evaluation techniques are really inadequate to capture the drivers of urban temperature variability. So in the beginning of this thesis, I asked the question, how does temperature vary within the urban heat island? How does urban temperature vary during heat waves? And finally, what causes urban temperature variability? And I think we didn't completely answer some of these questions explicitly, but I think we're starting to put some numbers on this. So for example, how does temperature vary within the urban heat island? In our two studies, we've seen that this goes from order of magnitude 1 degree to order of magnitude 5 degrees, but we certainly haven't seen temperature variability in surface air temperature of order of magnitude 10 degrees or larger, which is what's reported in the literature for land surface temperature. Finally, how does urban temperature vary during heat waves? Answers, it often decreases. Again, it's, urban temperature only increases about 0.9 degrees for every degree that rural temperature increases. And finally, what causes urban temperature variability? We've confirmed that in all these sites, a significant amount of urban temperature variability seems to be driven by surface properties, and in particular, in cities we've looked at, this often includes vegetation. It's a significant cause of spatial variability in surface properties. So there's a couple of implications for some of this work. So first of all, we talked about this a little bit more. So land surface temperatures, including vegetation, et cetera, drive this temperature variability in the urban heat island, which has associated ramifications for our policy partners on some of these studies. We think that this result shows that satellite-driven land surface temperature, which is often used by policymakers and planners because it's readily available, is pretty cheap if you're a non-commercial entity because it's free. Using these as a planning tool can actually cause you to miss or exaggerate urban hotspots. So exaggerate in the case of Baltimore and entirely miss in the case of a city like Nairobi. Then an implication from our third chapter is that our work suggests that absent changes in circulation or urbanization, and these are like big ifs that are probably not going to happen, climate change may not exacerbate urban heating. And so this is certainly something that finding that wouldn't hold for Asia or like a rapidly developing part of the world, but in the United States, where the urbanization has sort of leveled off over the past several decades, we think that this might be something to look for. This in turn suggests that if people are looking to work with heat and health, they shouldn't just focus in urban areas. Finally, we've shown that care must be taken when using numerical models to assess urban heat island mitigation strategies, which is the most common thing that you see as a motivator for undertaking these studies when you go through the literature. Every one of these papers begins with, oh, well, people in policy and government need to understand what they're supposed to do. So like we did this model and like check our model, like our root mean square error is less than 1. Like therefore you should paint all of the roofs in your city white. like these are actual conversations that happen, or like, you know, you should change the cladding of your building, and then the one architect who like happened to be walking by is like, that's not legal, like don't do that. So you can really start to go astray in places where, you know, you think that you have been very good. So I would like to acknowledge a lot of people in this room. In particular, I have to thank my funding, the Earth and Planetary Sciences Departmental Fellowship, IGERT, thanks Grace, and the NIHS grant, whose number I always forget, that Ben and Julia Golke have been on. I have to thank my committee, of course, Darren Waugh for being a tremendous advisor, Ben Zychek for also being a tremendous advisor and also picking up the tab, and Anand Kanhata-Desikan for being a terrific collaborator and advisor for these years. I'd also like to acknowledge the Waugh Research Group, and you guys aren't sitting together, so I can't acknowledge well. So Olga and Caesar, Engage, Will's here maybe. Yeah, there's Will, Molly, hey, everyone else. I've been really lucky here to have like an amazing amount of collaborators. Like I look around this room, and it's like one person out of every couple is someone that I've worked with, either on paper or on a study or at meetings. I was taking me onto the field, and you guys have just been so wonderful, and so I thank you from the bottom of my heart. I have to thank Jan for coming to the United States with me, dealing with the immigration system. So thank you. Your support and your collaboration has been really helpful. I have to thank my family who's here, my parents and my brother, sitting over there, for coming, sponsoring the food, possibly later, as well as all of my wonderful, wonderful friends. Thank you guys so much for coming out and supporting me. It really means a lot that everyone has come out. And so with that, I'm going to leave these here, and I'm open for questions.
Okay, and is open for questions. So, any questions?
Kathy.
So there was somewhere a slide back then that was showing the health, some kind of a temperature for health.
Yeah.
That was 20-some degrees. Where is that number?
Yeah, so that was where they found a significant, so you look at the dose response curve, which I like struggle to understand what that means, but essentially it's the saddle point of where they found a statistical relationship between mortality and like excess death. And it's important. It's a very low temperature. We were really skeptical about some of this, but it's important to keep in mind that, so first of all, they found that only for vulnerable populations, which includes the infants and the elderly. And it's also maybe worth noting that in this area, there's very high rates of HIV and AIDS prevalence. So there's a lot of people who are really immunocompromised. But I suspect a lot of that has to do with, you know, like really young babies or older people. But yeah,
that was also a mean temperature.
Yeah, that was a mean daily temperature.
It's a threshold for a curve fit. So they're finding a temperature effect going back, and it's where you hit zero. So it may not be meaningful till you get well above that.
But I would think the elderly would, you know, say living in a house with one warmer temperature is not going to see.
Again, I mean,
I certainly do.
Yeah.
Yeah, and I mean, I think that's what's hard to judge. Like this is, you know, this is an area that has so little data. Again, that's 20 degrees, but measured at a weather station. So we suspect what's going on is they're measuring temperature at like the Army, you know, like barracks, which they might have cited in a nice place. And then they're measuring the health effects in these neighborhoods, which could be 5 degrees or even higher, depending on some of these heat waves. So we think it's maybe one of these two things. There's certainly many people in this room who could comment a lot more on like global health and epidemiology than I could. But I suspect that like to comment on that, like the physical basis for that, that's sort of what we think is going on, is that they're taking a measurement in one location and it's really reflective of another temperature.
So when you're looking at the regressional coefficient between temperature and is it like most of the low values like out west.
Yeah, and so
Did you hear any idea what that might be?
yeah, so I mean, again, a lot of those cities that are, first could be coastally influenced or desert cities, or cities where some of our assumptions don't hold. So first of all, we're thinking a lot about minimum daily temperature. In sort of desert cities in the Southwest, you'd actually expect that minimum daily temperature differences would be pretty small compared to the daytime differences because of what's called the urban oasis effect. So you have like irrigation in cities that allows the cities to be cooler during cities. So that's probably why desert cities wouldn't really capture this effect. The other one is I think some of the coastal cities, like there's some different differences in like humidity that may modulate some of the nighttime cooling. We have seen these results for daytime temperatures as well as nighttime temperatures. So I think I wish I had it queued up here, but I think maybe a better way to look at that would be to see, compare the daytime and nighttime effects in those cities. Oh.
So the mortality rates change at different temperatures. So I'm thinking of the north of the you get high mortality.
Yes. So generally, we see higher mortality for heat, at least in some of the more northerly parts, which is like a little bit counterintuitive, but it points to perhaps, people aren't used to it. It's sort of like the dumb way of saying it. Whereas, this isn't entirely the case. Like some of our work in Alabama has worked at identifying some of the impacts of heat in southern locations where it's perceived to be less of a problem. It's worth pointing out for any and all mortality statistics for things that have been done, I think, for like the new ICD 9 or 10 codes, like the data on what causes heat, like, people show up at the hospital, and if they're experiencing many of the symptoms that are associated that we know get worse with heat, it doesn't get checked as like, oh, it's really hot, this person is ill because of that. It often gets checked off as something else. So teasing out like what causes this is actually can be somewhat difficult. But to answer your question, generally, people have seen that northern populations are really not ready for heat waves. And I think that heat wave I talked about in the beginning of Russia and Eurasia in 2010 really, really illustrates that. Yeah, definitely.
I guess I'm just wondering what's the impact of cloudiness on same conditions, very cloudy.
Yeah, and that's something that I wish we'd been able to dig into with the model, and had, I guess, the model done a better job. Maybe we could have, but we think that some of that variability we saw in urban-rural differences when it got warmer, we link that to weather conditions. When it's drier out, there's definitely no clouds. We think that therefore, what's causing that, the decreased urban-rural temperature differences during warmer conditions is related to atmospheric water vapor, which could either be like a humidity effect, or it could be clouds. Just doing some back of the envelope calculations, like it's probably clouds, just because that there's more of them. They alter the visibility a little bit more, but it could be maybe a little bit of both. So I think clouds are probably an important part of the story, but one we unfortunately didn't have a really good way to. Yeah, and again, I'm talking mostly about the outgoing long-wave radiation rather than the reflected incoming short-wave radiation. But yeah, definitely.
Have you thought anything about, they always put out heat index. I mean, that's temperature and humidity. And that certainly fits with my experience that 105 when I went to Phoenix did not feel worse than the 98 when I lived in Houston. Have you done anything at all?
Yeah.
Combining, or thinking at least about combining?
So I showed results in Nairobi. I can go back to. So in Nairobi, oh, there we go. We looked at the heat index, which is shown here in units of Fahrenheit. And you can see that these two curves look pretty similar. So looking at that, I felt like this didn't really add any additional information, and humidity might be something that wouldn't be available. It's an additional variable.
Nairobi is high and dry. You're on a 5,000, 6,000 foot plateau. Might not be an effect there.
I mean, it depends.
Might be a bigger effect in Baltimore.
What time of year? Yeah, so we have looked at that in Baltimore. And what we've seen in Baltimore is actually, the scale that we're looking at, the places that are hotter are also drier. Surprise, surprise. And so actually that effect sort of balances itself out. And so we actually don't see, the temperature data seems to be telling us something a little bit different than the heat index. But I think maybe to get at the larger point behind your question, which is how can we understand heat exposure from using meteorology, the temperature just gets at how fast molecules are moving around together. Whereas as humans, we experience heat in a whole, a variety of ways. And I think one important one is sun, which is an important factor. So between wind speed and sunlight, I think those are probably things that would be more important to throw into the mix. When I talk with community members about these results, I think they always are really disappointed to see that we see such small differences between some of our sites. Particularly for folks, who are like, no, it's definitely 10 degrees cooler when I go into a park or a forest or whatever. And I think a lot of that is really just shade. We all feel it
Shade
too.
makes a huge
Right.
difference.
And
I
that's
always
something
think of
that
evaporation potential. I get overheated very quickly, and then relative when it's hot and relative humidity is up there, so I can't evaporate any sweat. That's why a breeze feels good. It helps.
Yeah, definitely. And that's something that our thermometers don't really capture. But in some cases, some of us were a little bit driven by the availability of instrumentation. So getting something that does a wet bulb load measurement, which might be something that's more like you're at, would be harder to do just in the spatial scale we're looking at. But I guess I'd throw that up as a future work suggestion.
Okay, so that'll, I'll just describe how this works. So we're going to thank Dana again, and then we're going to ask all the non-EPS faculty to leave the room so we can have a short defense parts. But don't go too far away. So we'll thank Dana again.